welcome to today's session. In this session we are going to discuss steady state probabilities in Markov chain. The main agenda is recap what is Markov process and transition probability metrics, stationary distribution of Markov chain, and finally we will discuss some problems related to stationary distributions. So in the last session we have discussed what is a Markov process. A Markov process is a special type of random process which satisfies a Markov property, namely the memoryless property. Whatever things happen to the value of x of t during the past time is invariant, or it is insignificant for the current value of x of t, or simply current value of x of t just depends on the just preceding state value. That is another wonderful property of this Markov process. But pure Markov process or pure Markov chains are difficult to see in physical situations. Almost Markov chain or almost continuous Markov chains are observed. So we are going to define what is steady state probability. A steady state probability means the probability that a Markov process will not change its probability after a long time, or after a particular stage the state probabilities become invariant because it is not affected by the transition probability matrix TPM. So let capital X be a homogeneous Markov chain with the transition probability matrix capital P if there exists a probability vector capital pi such that pi p is equal to pi. That means this p has no role on this pi, and definitely this pi is a probability vector, so total probability should be 1. Then that probability vector pi is called the stationary distribution or steady state distribution or long run distribution of the Markov chain. Then we are going to discuss a simple concept, regular metrics. Any stochastic or Markov matrix capital Phi for which p raised to n, the nth power of this p has all positive entries for some positive integer n, is called a regular matrix. If this n is equal to 3, it is called a 3 regular. If that n is equal to 10, it is called a 10 regular matrix. Now we are going to state a theorem. This theorem states under what condition there exists a steady state probability distribution for a Markov chain. Let capital be the transition probability matrix of a regular homogeneous finite state Markov chain. Then limit n tends to infinity p raised to n is equal to q. Then that q is a matrix whose rows are identical and equal to the stationary distribution capital pi for the Markov chain. If this limit n tends to infinity p raised to n is equal to q, that means as n tends to infinity, the power of p to n gives a matrix q. That q gives the steady state probability distribution of the Markov chain. Then we are going to discuss a simple problem. If the transition probability matrix of a Markov chain is p is equal to matrix 0, 1, 0.5, 0.5, then find the steady state transition of the chain. We have to find the steady state transition probability. That means the probability vector which is invariant with the transition probability capital P. So we use the long run probability formula. Pi p is equal to pi and total probability sigma pi is equal to 1. So this p is a 2 by 2 matrix, so capital Pi should be a 2 state vector, pi 1 pi 2. Then pi 1 pi 2 into matrix p is equal to pi 1 pi 2. Then we apply matrix multiplication, take this row and multiply the first column and do the same thing for the second column. So I've got 0.5 pi 2 is equal to pi 1 and pi 1 plus 0.5 pi 2 is equal to pi 2. And one more condition, capital Pi is a probability vector, so total probability equal to 1. We solving these three equations. That means we substitute 0.5 pi 2 is equal to pi 1. Instead of pi 1, put 0.5 pi 2. So we got an equation in pi 2 itself, from which we got pi 1 and pi 2. Here 1.5 pi 2 is equal to 1, so pi 2 is equal to 1 by 1.5. Actually 1.5 is 3 by 2, so 1 by 3 by 2 is 2 by 3. Now use this relationship. So pi 1 is equal to 1 minus 2 by 3, that is equal to 1 by 3. So the steady state transition probability or long run probability pi is equal to 1 by 3, 2 by 3. It means as the time goes on, the first state become the probability 1 by 3 and state the 2 has the probability 2 by 3. That means the state 2 has more probability to occur. The Markov chain will take the state 2. It will land on state 2 with higher probability. That is the meaning. Now we discuss a problem with higher dimension, that means 3-state problem. Assume that a computer system is in any one of the 3 states, busy, idle and under repair respectively, denoted by 0, 1 and 2. That means 0 means it is busy, and 1 means the system is idle, and 2 means the system is under repair. Observing its state at 2 p.m. each day, we got the transition probability matrix P is equal to 0.6, 0.2, 0.2, 0.1, 0.8, 0.1, 0.60, 0.4. And see that the total probability in each row should be 1. 0.6 plus 0.2 plus 0.2 is equal to 1, like that should be there. Find the third step transition probability matrix. Third step transition probability matrix, that is P3, P cube, and also determine the limiting probability, that means long term probability measure. First of all, we find out third stage transition, that is P3, that is equal to P cube, because the Chapman-Kolmogorov theorem states that P raised to 3, that is P cube, is same as third state transition probability. The transition probability matrix will satisfy the matrix power rule. Then P cube is equal to the transition probability matrix into this matrix into this matrix. Multiplication 3 times this matrix multiplication, we got this result. We move on to the long run probability. In that case, we start with the long term probability formula, pi p is equal to pi and total probability sigma pi is equal to 1. Here this problem has 3 states. The computer system has 3 states, and so pi 1, pi 2, pi 3 will be the states for the long run. As usual, we calculate pi p is equal to pi here, pi 1 into 0.6 plus pi 2 into 0.21 plus 0.3 into 0.6 equal to pi 1, like that. Now we can take this pi 1 to the left side, so we got 0.6 pi 1 minus 1 pi 1, that is minus 0.4 pi 1, like that. So it becomes a homogeneous system of equation along with this additional condition. Then solving these 3 equations, we got pi 1 is equal to pi 2 and minus pi 1 minus 0.5 pi 2 is equal to minus 0.6, and we use pi 2 here. So pi 2 is equal to 2 by 5. Then pi 1 is equal to pi 2 condition, so pi 2 and pi 1 should be equal to 2 by 5. And by the normalization condition, total probability pi 1 plus pi 2 plus pi 3 is equal to 1. So we can calculate pi 3 by subtracting sum of this pi 2 and pi 1 from 1. That is 2 by 5 plus 2 by 5, that is 4 by 5 from 1, that is 1 by 5. So the long run probability vector capital pi is equal to 2 by 5, 2 by 5, 1 by 5. That means in long run, state 1 or state 2, that means busy or idle, have equal probability, but under repair state has lower probability, only 1 by 5. So one more problem. A housewife buys 3 kinds of cereals, A, B and C. She never buys the same cereal in successive weeks. If she buys cereal A, the next week she buys cereal B. However, if she buys B or C in current state, the next week she is 3 times likely to buy A as the other cereal. In the long run, how often she buys each of the 3 cereals? Since the problem is to find the long run probability, we start with the long run probability formula, and before that we have to formulate the transition probability matrix. In this problem, there are a lot of conditions are given in the form of words, so we have to formulate the transition probability matrix or TPM first. Okay, this is the current week, this is next week. Suppose she buys the cereal A current week, next week she will not buy A. So in the given statement, it has given that next week she should buy B if she buys A in the current week. So next week she will buy B. So total probability is 1. Total probability for the next week for this A is 1. Now in the current week she buys B. So next week she will not buy B. And one more condition, the probability to choose A is 3 times than the probability to choose C. And the normality condition when we apply the total probability should be 1. So if you choose 1 by 4, then definitely it is 3 by 4. We cannot choose any other probability other than 1 by 4. We apply the same condition for C. If she buys C, she will not buy C in the next week. And the probability for buying A next week is 3 times than that of the other. If she buys C, the current week, the next week she buys A or B. And so the probability for B is 1 by 4. Then only we can make 3 times the probability for A, and total probability for the C row should be 1. So this is the transition probability matrix. Now we choose the condition pi p is equal to pi with total pi is equal to 1. Here also there are 3 states, so I choose pi 1, pi 2, pi 3 as the Longrun probability vector. I repeat the matrix multiplication, pi 1 into 0 plus pi 2 into 3 by 4 plus pi 3 into 3 by 4 is equal to pi 1. And there is no pi 1 in the left side, we have pi 1 on the right side. So we got pi 2 into 3 by 4, 3 by 4 pi 2 plus pi 3 into 3 by 4, 3 by 4 pi 3 is equal to pi 1. Then we multiply this equation throughout by 4, we got 4 pi 1 minus 3 pi 2 minus 3 pi 3 is equal to 0. I also take other equations and simplify. Pi 1 plus pi 3 by 4 is equal to pi 2. Multiply by 4 and simplify. 4 pi 1 minus 4 pi 2. 4 pi 1 minus 4 pi 2 plus pi 3 equal to 0. And from the third equation I got pi 2 by 4 is equal to pi 3, or pi 2 is equal to 4 into pi 3. And one more normalization condition, pi 1 plus pi 2 plus pi 3 is equal to 1. So we have 4 equations, 3 equations from the matrix, 1 is the normality condition. Using these 4 equations in 3 unknowns, we can solve like this. Pi 1 is equal to 15 by 35, pi 2 is equal to 16 by 35, and pi 3 is equal to 4 by 35. We should remember the total probability for pi, that is pi 1 plus pi 2 plus pi 3 should be 1. Here it is correct. 15 plus 16 plus 4 is equal to 35, and 35 by 35 is equal to 1. So in long run, the serial A will buy with the probability for 0.4286, serial B with the probability 0.4571, and serial C with the probability 0.1143. So the highest chance is for serial B. In long run, this particular housewife will buy the serial B. Its probability is high. Okay. So thank you very much for the patient listening. The important takeaways of this session is actually what is the steady state probability of a Markov chain. What it says, the steady state probability says that in long run the probability remains steady, and that steady probability will tell you what will happen in the future. What are the different probabilities for various states in the random process. That is a useful idea for most probably the movement of robots. What happened after certain stage, this robot's motion will result. If the robot will start from this particular starting point, and after 100 moves, what will be its position? What is the probability that that robot will stay at that particular point, or will do this particular action, etc. This type of modeling and this type of predictions, and more precisely this idea, the Markov chain, the discrete time Markov chain, will help us to utilize more thing related to the predictive analysis. Thank you very much.